Welcome back, Cubs. In this video, we're going to introduce Chapter 10, States of Matter, starting with the first section lecture. So you can follow along and find the lecture notes under the topics page, Chapter 10 lectures right here. So States of Matter, this is one of the easier chapters. A lot of this is going to be review for you guys, but we're going to add one layer to what you've previously learned with the kinetic molecular theory. So kinetic molecular theory deals with three states of matter: the solid, liquid, and gas. And scientists were able to extrapolate what was happening down at the molecular level based on the observations at the macro level. So this theory, it's based on the idea that particles of matter are always in motion. Make sure you know this here. That will be one of the questions for the chapter exam. And it's based on an ideal gas. So an ideal gas, it's not a real gas. It's a hypothetical gas that perfectly fits all five assumptions of the kinetic molecular theory. In a couple slides, we'll talk about the difference between an ideal gas and a real gas. So there's five assumptions. You need to know these five assumptions of the kinetic molecular theory. First assumption is that gases consist of large numbers of particles. Remember, we're dealing with Avogadro's number amount of particles. So 6.022 times 10 to the 23rd, a huge amount of particles. And they're relatively far apart, which means that most of a gas is empty space. So if I were to take a balloon and blow it up. So although there are gas particles inside of the balloon, inside of here is mostly empty space. Same thing with the air in the room. You can easily wave your hand through the room because it's mostly empty space. Second assumption, the collisions between the walls of the container and the gas particles, those are going to occur. That's going to increase pressure. More collisions would be more pressure. Definition here, elastic collisions, that means that there's no net loss of kinetic energy. So elastic collisions, think of two billiard balls when they hit each other, they bounce off. An inelastic collision would be like two balls of gum that when they collide, they kind of stick together a little bit. An elastic collision would be like the billiard balls. So there's no net loss of kinetic energy. The third assumption, gas particles are in continuous, rapid, and random motion. So that means the particles are going to be moving around the shape of the container. For example, if you have a bonfire out back, your neighbors will be able to smell the bonfire because those gas particles are in continuous, rapid, random motion. Kinetic energy is greater than the attractive forces between the particles. So that means although the particles might be attracted to each other, the kinetic energy is greater, therefore not causing the particles to stick together. Number 4, there are no forces of attraction between gas particles. This is for an ideal gas. Remember, that's a hypothetical gas. It's not a real gas. We'll talk about that in a moment. So that means gas particles act as billiard balls bouncing off of each other. So they're not going to stick to each other. But we learned previously that there's something known as intermolecular forces. These are the forces of attraction between molecules. We had dipole-dipole, we had hydrogen bond, London dispersion force, and induced dipole. So with real gases, we do have some attraction. And the fifth assumption, the temperature of a gas depends on the average kinetic energy of the particles within a gas. So if temperature goes up, the kinetic energy goes up. If temperature goes down, the kinetic energy goes down. We can determine the kinetic energy with this equation here. Some of you might have learned in conceptual physics. It's 1/2 mass times velocity squared. That'll give us the kinetic energy, which is measured in joules. The mass, we're going to use grams, and the velocity will be meters per second. So temperature increase, the velocity and kinetic energy increase. If temperature goes down, the particles start slowing down and the kinetic energy decreases. Think of if you have a balloon and then you put it in a cold environment. The balloon's going to deflate because the kinetic energy is decreased because the temperature went down. Also, this is important here. At the same temperature, lighter particles will move faster than heavier particles. So that means hydrogen gas would move faster than oxygen gas. Lighter gases move faster than heavier gases. That's related back to this equation, Ke equals 1/2 mv squared. So gases, they don't have a defined shape or volume. They fill the container and take the shape. So once again, the balloon, if I blow it up, takes the shape of the container. The balloon expands because I'm forcing particles inside the balloon. Those gas particles are bouncing off the walls of the container. And in the next chapter, we'll talk about things like volume and pressure and temperature with a mathematical equation. They're also fluid. So gas particles will slide past each other. Gases and liquids are referred to as a fluid because the substances, they flow, they can slide past each other. That's why you can swim through water, or you can easily move your arms in the air. But it'd be pretty difficult to move your hand through a solid object because of what is happening at the molecular level. Gases are incredibly low dense. They have low density. So particles are far apart at atmospheric pressure unless they're compressed. So some gases, they have a low density. So we can also see this low density here with an example. Okay, so we talked about density of gases. Here I have a birthday balloon from my birthday back in March. It's still inflated with helium. We can see that the balloon is less dense than the surrounding air, and it floats up. So, lighter density here versus the balloon. If we tie off the end of the balloon here that I filled with air, okay, we have two balloons. Let's determine the density. We see that one balloon sank and the other floated up because of the difference in density. Okay, so gases. Gases are compressible. Like this balloon, I can squeeze it down. Squeeze it down. If we decrease the volume, we see that the pressure will increase. Here we have a schematic of if we decrease the volume, if we press down on this, notice what happens to the number of collisions with the walls of the container. The collisions with the wall of the container increase, therefore the pressure will also increase. Then we have diffusion and effusion. So when gases combine, the gases will mix without being stirred because they are in constant random motion. And then effusion, that's the process by which a gas particle will pass through a small opening. So with this mylar balloon here, there's some very small openings that we can't really see without the use of a special microscope. But this balloon was fully inflated back on March 14th. However, over time, some of the gas particles effused out through these very small openings in the mylar balloon. And the balloon's not as full as it was back in March. So effusion occurs when a gas passes through a small opening. Now this relationship with real gases versus ideal gases. So the noble gases, those are the closest to ideal gas. So think of some of the characteristics of the noble gases. They have 8 valence electrons. They have an octet of electrons in their outer shell. They're relatively non-reactive. Because they're non-reactive and they have a full valence shell of electrons, they're also nonpolar. So nonpolar would make it closer to an ideal gas. So the greater the polarity of a molecule, the greater attraction. That means polar molecules like ammonia gas or water vapor, those are going to deviate from the ideal gas because of their greater polarity and greater attraction. All gases, regardless if it's polar or nonpolar, they're going to slightly deviate from the ideal gas law. And then this will be one of your multiple choice questions. So at very high pressure and very low temperature, the overall kinetic energy drops and cannot overcome all the attractive forces. So that means when you force the molecules closer together and you increase the pressure, that means there's going to be more interactions between the molecules. Also, when you lower the temperature, the molecules, they become a little bit more sluggish and they stick together a little bit. So that means the kinetic energy is going to drop and it's not going to be able to overcome all of the attractive forces. So there's a couple homework questions for you guys to do from the book. Let me or Mr. Bonventre know if you have any questions. We're starting a new discussion board for this chapter, chapter 10, but you can also use email and remind for those questions. Okay, have a great day, Cubs.